In this video, we'll dive deeper into retrieval augmented generation. We will take a look at some common issues that we encounter when trying to implement RAG systems in the real world, and we'll look at some of the most common solutions, such as self-query and parent document retrieval. We'll then finish by taking a look at a very interesting approach called HyDE. But before we look at all of this, I thought it would be good to spend a few minutes talking about how we train embedding models for sentence similarity. The training process for sentence embedding models often begins with a pre-trained language model like BERT or GPT. These models have been trained on extensive text, giving them a robust understanding of language. We fine-tune these models to output embeddings that can be used to perform semantic searches. One training approach relies on using the inherent structure of data to teach the model which sentences are similar and which are not. For example, sentences from the same paragraph or similar articles could be considered as similar, while those from different topics are treated as dissimilar. Another approach involves working with semi-structured data. For example, researchers at Microsoft trained the E5 embedding model by curating a dataset called CC pairs. This contains pairs of queries and passages relevant to the queries. These pairs are built from diverse sources, such as Reddit, where a comment is a direct response to a post, and Stack Exchange, where the upvoted answer is a high-quality response to the question. In the fine-tuning stage, the model is trained using these datasets with a loss function like contrastive loss. Contrastive loss is a technique used to learn embeddings by bringing similar items closer and pushing dissimilar items apart. In the context of sentence embeddings, this means that sentences with similar meanings are pulled closer in the embedding space, while those with different meanings are pushed apart. Let's now look at some practical strategies to improve the efficacy and accuracy of RAG systems in the real world. One such strategy involves the use of the so-called self-query retriever, while the other strategy involves the use of the so-called parent document retrieval. When designing RAG solutions, there is a natural tendency to rely heavily on semantic search. As we have seen, this technique proves very effective for identifying passages that share a semantic connection, even in instances where the exact wordings differs. However, this approach has its limitations. Imagine a RAG system that holds an extensive database of books, including various metadata, such as publication dates, authors, genres, and plot summaries. Now, let's say a user poses the question, what is the earliest published work by Stephen King? In this scenario, the effectiveness of traditional semantic search is limited. The query specifically requires information that is more accurately retrieved from the system's metadata, particularly focusing on the author's name and publication dates of the works. Self-query in this context refers to the system's ability to recognize when it should pivot from relying solely on semantic search to directly querying its metadata. When a RAG system employs self-query, it essentially conducts an internal assessment to determine the most effective method for retrieving information. It analyzes the nature of the query and decides whether to proceed with a semantic search or to directly interrogate specific metadata fields. In the case of the Stephen King's query, the system will recognize the need to access the metadata detailing book release dates rather than searching through plot summaries. This self-query mechanism enhances the flexibility and accuracy of RAG systems, enabling them to adapt their retrieval strategy based on the query's requirements. Another issue is the way we segment text into chunks. Blindly splitting text into chunks of the same size risks breaking text across semantic boundaries, for example, mid-sentence. As a result, embedding vectors might contain a weaker signal, and the chunks might not include sufficient context for the LLM to effectively answer queries. Using a semantic understanding or even simple heuristics like splitting by paragraph boundaries instead of fixed-size chunks greatly enhances RAG systems. Another related issue is how large we make the text chunks. We typically prefer smaller chunks. The reason is that smaller documents can be more precisely embedded, meaning that their semantic content can be more accurately represented in a vector space. If a document is too long, its embedding may become less meaningful, diluting the specific information it contains. On the flip side, it's important to keep documents long enough to retain the context of each section. Without sufficient context, the information in these chunks might be misunderstood or decontextualized. This is where parent document retrieval comes into play. The system starts by splitting large chunks into smaller chunks. This ensures that the embeddings for these chunks are precise and meaningful. When a query comes in, the system initially fetches these smaller chunks based on how closely their embeddings match the query. Then it returns the larger parent chunks to the system so that they can be included in the context of the LLM to answer the query. By doing this, it reintroduces the broader context that might have been lost when the document was initially split into smaller chunks. In essence, parent document retrieval is like having the best of both worlds. It uses the precision of small, well-embedded chunks to locate relevant information efficiently. Then it draws on the broader context of the parent documents to ensure that the information is well understood in its full context. We'll finish by looking at a very interesting approach called HyDE. HyDE stands for Hypothetical Document Embedding. When a query comes in, the RAG system prompts the LLM to generate one or more hypothetical documents related to the query. These are then embedded and used in place of the original query to search similar documents in the vector space. The idea is that the embedding of the hypothetical documents will be much closer in the vector space to potential answers, thus improving the overall performance of the retrieval system. We'll close this episode by taking a quick look at some of these more advanced retrieval strategies in practice. We are going to get started from the self-querying retriever. Now, here I've done a couple of imports and installs as usual, and you are going to need for all of these examples to set an OpenAI API key, and we're going to use GPT 3.5 Turbo for these notebooks. Now, the dataset we're going to use is pretty similar to the one we had just discussed in the theory part of this video. So it's just going to be a bunch of books with plot summaries and metadata. Let me go ahead and download that, and we can take a look. I had already downloaded it, but you can see what this is, just some metadata, title, author, publication date, and then the plot summary. So with this, we're now going to, as usual, load the contents of this file into Langchain document object. So the page content is going to be the plot summary, and this is where we're going to do the semantic search on, and then we've got the metadata there. So 20 documents, page content is a summary, and if we look at the metadata, that's Pride and Prejudice. Now, what we need to do here, as usual, we want to embed these documents, and we're going to use BG embeddings. So we pass the BG embeddings and the documents to Chroma to load all of them in the database. You will notice here that we did not split these plot summaries into smaller chunks, and that's because they are already quite small to begin with. So we don't always need to split documents into chunks when we want to do semantic search. Now, to the self-query retriever. The majority of this code is based on the official Langchain example documentation. I've just adapted it for the book's dataset. So number one, we need to provide the system with the list of attributes and a description and type. And then we want to provide a content description. So what's actually contained in the document page content, so that the system knows what to do with it. And then we initialize the self-query retriever with all of these information, so the metadata and the document content. As usual, we need an LLM and we instantiate it with temperature 0. We've already discussed this. Whenever we do RAG, we want to set the temperature to 0 because we don't want the LLM to be creative and hallucinate answers. We want to keep it as grounded as possible to the documents that we're providing. Okay, now that we've got our retriever, let's try it with a simple query. I want to read a book published in 1859. Now here, we do expect this to return one book, and indeed it returns the book with publication date 1859. This is A Tale of Two Cities by Charles Dickens. If we set the debug attribute to true and we run the same query, we can actually see what the LLM is doing. So Langchain is giving the LLM a very long prompt, which I'm going to try to copy and show you. So that prompt is pretty long, but here you can see that it is giving some examples to the LLM as to how it wants things to be queried. It's using some songs here, but then it's also providing the information we gave it. For example, the third example here is what we provided. This is the description of the metadata in the book and what it's actually contained in the plot summary, the content. So we've got this, and based on this information, looking at the query, which is provided at the end of the prompt, it generates this particular JSON string, which Langchain uses to understand that instead of doing a semantic search, that's what this query means, it should use a filter on the metadata. And the filter needs to look at the publication date equals to 1859. And of course, this returns correctly the only book that matches that. Now, let us try a different query. I want to read books with animals. So here we are expecting the LLM to determine that instead of using a filter on the metadata, it needs to use a query for semantic search. And indeed, the LLM produces this. You can see no filter and the query is animals. And the semantic search hopefully returns meaningful documents. So you can see here we have The Call of the Wild by, I think, Jack London. Yes, and that's obviously about animals. It also returns Animal Farm and other things such as White Fang. So this is working really well. Let us try yet another query. I want to read books about young people going on adventures. And again, this determines that we want to do a semantic search containing young people adventures. So this is going to be embedded and it's going to go into the embedding space to look for similar plot summaries. And it returns indeed the adventures of Huckleberry Finn. That's absolutely something that's relevant here. The Catcher in the Rye, something else which is very relevant. We're now ready to look at the parent document retrieval strategy. So here, notice that I am using a specific version of Langchain because I've had some issues with the latest version. I think they have inadvertently broken the parent document retrieval class. Hopefully they will fix it, but for now, this version works. So I am using the same dataset that we used for the first episode on RAG, which is the Huberman Lab transcripts. And so these are identical functions to transform that dataset into Langchain documents. And each of these has got basic metadata about the document, and then obviously the page content is the full transcript of each episode. Now, what we are doing differently here is using this parent document retrieval strategy, which aims to strike a balance between the precision of the embedding. So we want small chunks when we do the embedding so that the chunks are meaningful and we can find the relevant chunks based on a query. But we don't want the chunks to be too small when we put them or when we feed them into the LLM context, because if the sentence is too small, it might not have enough context for the LLM to be able to answer the question. So one way of solving this is essentially adding a layer, as you see in this picture, and we saw that before. So we take the episode, we divide each episode into large chunks, and then we divide each chunk into smaller chunks, and we embed these smaller chunks for the semantic search. So to do this in practice, I'm using a parent splitter, which is going to split the larger chunks 2000 tokens, and then the child splitter, so the smaller tokens are going to be 400 tokens, or the smaller chunks are going to be 400 tokens. And now that we've done this, we can simply instantiate the BG embeddings, the open source embeddings that I tend to use more often. And after those are imported, we are simply going to load all of these into the database. So I'm just going to run these and create a vector store. And then we're going to import the parent document retriever class. We're giving it the child splitter and the parent splitter. And we're not providing any documents yet, but we are adding the documents using the add documents function. Now, the parent document retriever is going to go through the documents and split them up as we have seen here. So it's going to do all of these for us automatically. We can, and this is going to take a while, of course. So I'll come back in a second. And when we are back, we'll take a look at how many chunks we end up with. So the documents have been embedded, and we have 1,759 small chunks. And we can see this in practice. We can go directly on the vector store and do a similarity search. For example, I'm going to ask what are the effects of apigenin on sleep, and this returns these 3 chunks or 4 chunks, which are very small. These are the small chunks because we are querying the vector store directly. However, you will notice something, that now there is an additional metadata, which is the document ID. So this has been added by the parent document retriever as it was doing the splitting. And this allows the retriever, whenever we ask it a question, instead of going directly into the vector store, it allows the retriever to give us the parent documents. So the same question returns much larger chunks, which are the parent chunks of these documents here. So that's how it works. And obviously, once we've got this retriever, we can use it as we did for any other retriever as part of a RAG chain. We'll close this episode by looking at the HyDE retrieval strategy in practice. We are going to use the same example as we used for the previous episode. So we're going to use the Huberman Lab transcripts. I've already run all of this code here, downloading the file, processing it into documents, and splitting it into chunks of 700 tokens. So that's already done. What we're going to do as well, we are going to get the BG embeddings. Okay, they are now downloaded, and we can use the HyDE retrieval system here. This is the original paper that talks about HyDE. I recommend to give it a read. It's very accessible and you're going to learn a lot in general about retrieval augmented generation. The majority of the code from here on is based on the Langchain cookbook. This is a beautiful part of the repository with a lot of examples, simple and advanced, of how to use Langchain for all sorts of things. And you can see here, if I look for hypothetical document embeddings, that's the notebooks with a lot of those examples. Again, I recommend you take a look at all of these. Now, to set this up, we need to instantiate an object of the hypothetical document embedder class, and we simply pass the LLM and the BGE embeddings, and then we need to give it a prompt. It turns out that the default web search prompt, which we're going to take a look now, works very well for hypothetical document embedding, because essentially it's prompting the LLM to write a passage to answer the question. So if we look at this in practice, we have the HyDE embedder, and if we call the embed query method on a query such as what are some good ways to increase motivation, what's going to happen in the background is that the HyDE embedder is going to prompt the LLM with this prompt to generate a response for this query, and that is going to be embedded for us. And in fact, you can see the prompt asking it to generate an answer, and you can see the passage that the embedder, that the LLM has generated in response. Now, why are we doing this? Again, the reasoning is that having generated a larger document, when we go and embed this document, is going to be much closer in the embedding space to the potential answers that exist in our database. And I have specifically chosen this query because if you recall from our last episode, the documents that were being retrieved in the vector space, that were closer in the vector space to this query, were not great to actually answer the query. The majority of stuff that came out was from the episode on immune system functioning, cooling, recovery, and in fact the answer was pretty bad. So let's say if using this HyDE retrieval strategy with these hypothetical document embeddings, we get a better answer. So how do we use this in practice? Well, first of all, we need to take all the documents that we have split, but this time we embed them with the HyDE embedder. This is going to take a little bit of time. Oh, and something else to point out here, which is counterintuitive. You would expect that the embedding that we use to embed the documents is not the HyDE embedder, but is the standard BGE embedding, because obviously we do not want to generate hypothetical documents. But again, the hypothetical document embedder exposes two methods: the embed query that the system uses to embed a query, which does the hypothetical document generation, and then the standard embed documents method, and this method will simply call the standard embedding or the baseline embeddings that have been passed to the constructor of the hypothetical document embedder. So let's see if everything has been embedded. Yes, everything has been loaded in there, so we can get a retriever out of this. And now we can see what relevant documents come back from this query. So you can see the hypothetical document part and the documents that have been returned. Now, immediately, I am much happier with this. You can see in the metadata that the documents returned are about how to focus your brain. The other document here is actually how to increase motivation and drive. That's another chunk from the episode How to Increase Motivation and Drive. So it is much more likely that these documents are actually related to our query rather than, again, these documents here, which were not very related to the query. So we can now take this retriever and bundle it into a full RAG chain as we did before. And we'll now ask the question. And again, it will answer this question using those documents. And hopefully the answer we get is much better than the previous one. One way to increase motivation is to celebrate your wins, but not every win. By selectively rewarding your behavior or performance, you can maintain a healthy level of motivation without experiencing a dopamine crash. Additionally, it can be helpful to set intermediate goals and not overly celebrate each of them. Now, this is such a good answer. I have actually listened to the podcasts, and that's a very, very good summary of what was discussed in those podcasts, as opposed to these, which is mostly unrelated to the query we asked.